Okay, thanks everyone for joining. We're gonna go ahead and get started. I want to thank all of our panelists for being here. We're very excited for this final day of workshop activities. So thanks for joining so early in the morning for some of you. So for this series of short talks, we're gonna start with Sergio Leon-Rios. Sergio is a seismologist and postdoctoral researcher at the Advanced Mining Technology Center, where he's applying local earthquake tomography to better understand the distribution of critical mineral deposits in Chile. He also is interested in the cultural value of old seismological records. So without further ado, Sergio, the floor is yours.
Thanks, and thanks for this opportunity to show this work. There it is. So what I want to show you is a couple of findings of historical paper seismograms and related more to the history of Chile in September 73. So I titled this presentation as you can see, decoding the narrative of the Chilean coup d'etat through the seismogram of September of 1973. One thing I want to highlight is this is an interdisciplinary work with people working from the seismology side, also collaboration from the library of the department, but also from the university as well, and two artists that are also involved in this project. So in short, the agenda goes like this. Just as a summary, what we have here, like historical records at the geophysics department of the Universidad de Chile, the findings of the seismogram of the 73, then a bit of analysis of the signature that we found in the seismogram of, that left the coup d'etat, and what opportunities these records have opened in this short time. So just a brief summary, because later in the next few talks, the other Sergio working here is going to show with a bit more detail or with better photos what we have in the warehouse of a geophysical department. But in short, we have local seismic records for most stations in Chile. We have also a lot of paper mail with the correspondency with the other global institutions sending seismograms. We also have seismic bulletins with the earthquake reports, or also with all the station service for all the stations that were running in the old times. As you can see here in the photos, we have a smoke paper. We have a photographic paper. Also, here's a bit of correspondency, and most of the records are stored like this in boxes, and some other are stored like this in the top left corner, like wrapped in paper. In overall, they are well preserved, but we need to do a better inventory to know exactly what we have, and from there start to explore more in detail this legacy data. Another photo. And as I said before, and as the introduction said, I'm in this part, I'm more focused on the heritage, in the cultural value of this scientific data. Not interested right now in exploring a specific earthquake, but to put all the records in value as a scientific heritage. So to do that, and this is where the artistic component enter like in a more strong fashion. We prepare a proposal that we applied for the National Arts Foundation, and the translation is Seismic Heritage, which aims to prepare an artistic exhibition about heritage, earthquakes, and tsunamis in Chile. And the idea of this is to put in value or put value in all of the records, and also incorporate all of the tsunamis, like those stamps that you can get from Paleo Trench. And in the look of some sort of inventory of what we have here in the department, and also because last year we were commemorating 50 years from the coup d'etat in Chile, is that we found these seismic records that you can see here in the photo for the Santiago Seismic Station in 1973. So in the photo, you are seeing all of the 73 records. As you can see, they are well preserved, 3 components, photographic, this is a thermosensitive paper. So we start to look and see, okay, we have this very important date in the Chilean history. Let's have a look on if we can find the signatures of the coup d'etat. So focusing on September of that date, a bit of context. The stations, the seismic station was a geotech telebeam seismometer, a short period of 1 hertz. As we got the report that it was sent by the time in 76. This was sent to it wasn't the USGS, but an agency in the US that was collecting the stations that were operating around the world, I guess. And here we found the report from April 76, where it gives all the details of the sensor that it was installed. And this was installed around 2 kilometers from La Moneda Palace, close to where the campus is now, and also close to 2 army bases that were open at the time. Now they are museums. So what you're seeing now, it's in correlative from top to bottom, September 10, 11, and 12. And the main thing you see here when we put the vertical component only, it's this change in color, if you want, in the thickness of the traces that you can associate with the date and night. And in the next slide, you will see our interpretation of this, which show more clear this process. So you have the night from the 9th to the 10th of September, then the daytime. So Santiago wakes up. We have traffic, more people commuting to their work, etc. And then we have again the nighttime, the city rest, a bit of quiet around the station, and then again for the 11th September, the city awakes again. We have more activity related to commuting, etc. But still, we start to notice a difference between the 11 and the 10 in terms of the amplitude of that noise, and also in the length. And this solid black line shows the moment after the bombing of the La Moneda Palace, where the military took the power and set a national curfew. That similar to what happened with the pandemic, with the COVID-19, you see how the city goes to complete quiet, and in there you can see like earthquakes occurring in the traces that are clearly noticeable, but also the anthropogenic noise almost disappeared. Yeah, and that is caused by the curfew. If we look closer to the dates and to the time where the bombing occurred, like in the 11th September 1973, we have the archives from the Memory Foundation and Human Rights that describe with very well detailed the events. And so we know that at 1552, the airplanes begin the bombing of La Moneda Palace. And we know also that the attack continued for 16 minutes. We also know that a lot of vehicles were mobilizing from the army base we have here close to the campus towards the palace. So there was a lot of movement happening close to the stations. And we had these anomalous signals. We cannot directly associate it with the bombing itself, but at least two of them are in the time window of the bombing, and they are showing like a more anomalous signal than the rest that we can associate to the airplane flying at least, or to some bombing hitting the building. And the other signatures that you see here, that is wavering, these oscillations, we associate to the heavy army vehicles that were passing by towards La Moneda, but close to the seismic station. We are talking about tanks or heavy trucks, so it's a lot of noise that they are, or vibration they are causing. We summarize all of that in an article that was submitted to the Historical Seismologies column in the SRL. We are right now in the second round of revisions. We already submit the second round, so we hopefully will get news during, I don't know, mid-November, we hope. And this also helped us to get the assistance from the National Conservation and Restoration Council that will help us with guidelines and open access of these seismograms. And in addition to the records of the 73 coup d'etat, we are going to start the preservations for the 1906 and 1928 earthquakes that occur also here in central Chile. This is one of the pictures they sent, where the people working there in the council are starting to study and analyze for the component of the status, to make like initial diagnosis of the records, and then after that they will give us some guidelines of how to better preserve the data and also the paper itself. So a bit of take home. We're in the process of upgrading the historical records to the category of scientific heritage material. The finding of the seismological signature of this 73 coup d'etat provide a great opportunity for linking science and historical episodes, and well, open these historical records to other disciplines like art, have opened new opportunities for collaborations. So thanks for listening.
Thank you very much. We have a couple minutes for questions. If you have any questions for Sergio, please put them in the chat or the Q&A function.
Hi, Emily. Yes, have historians show any interest in your results? That's the question. Last week, I was in a art forum where I present this, and the reception was really good in terms of first of the artistic component, like in the traces itself, like in the thickness of the traces. But also the historians have communicated, and the idea of this is to first to open to a broad audience. So one of the things is to prepare a copy of the records and give them to the Museum of Memory and Human Rights Foundation, so they can have this seismological perspective of the historical episode. So yes, the interest is, I guess, after the publication of the article, I think it will grow. So yeah, I'm looking forward to for next year what's going to happen.
Thank you. We have another question from Tim Ahern. Do you have an estimate on how many legacy records you have?
Well, yesterday with Sergio, we went to the warehouse to check for that. We have an estimation. We are what, around 1940, something like that. But what is the number? Like the actual number, we don't have any idea so far. So that's one of the things we want to raise with this talk, with the talk that Sergio is going to give in a few minutes, is to get the attention and hopefully get some funding to start to get these answers correct.
Thank you. And then we have one last question from Virginie Durand. How did you digitize the waveforms, by hand or using machine learning tools? Do you do it for all the continuous waveforms?
So this is digitized, is just a scan. So the scan was made by the librarian service. They have this big scan machine that can take a high resolution photography. But then after that, we haven't digitized it itself, like to get each trace by separate. We want to test some. I guess this year, a few months ago, there was an article that was showing how to digitize the traces. So I want to give it a try to that. But the thing is, because we are dealing with anthropogenic noise, probably we'll find a lot of problem or issues. I guess it's easy when you are dealing with earthquake, where the traces are more notorious. But I want to try.
Thank you so much. Okay, in the interest of time, we're going to move on to our next speaker, but if you have any lingering questions, please feel free to put them in the chat or the Q&A function, and we will get to them after. Thank you again, Sergio, for that wonderful talk. Our next speaker is also Sergio Ruiz, who is a seismologist, an associate professor of the Department of Geophysics at the University of Chile. Thank you so much for joining us, and without further ado, the floor is yours.
Okay. Now, do you hear me? I'm sorry.
Yes, we can hear you and we can see you.
Hello. Hi, Juliet. Hi. Do you hear me?
We can hear you, yes.
Oh, okay. Oh, thank you. I'm sorry. Thank you for the opportunity to show the analogical seismograms that, well, Sergio introduced very well something of the data that we have here in the geophysics department in Santiago in the University of Chile. We have a warehouse with some old papers. This warehouse has some several years in this place, and in the last time we start to looking what we have. One of these is the work of Sergio that is looking for some historical events and looking for ambient noise, and also we start to look in some large earthquake what are in the data, but we are in a very preliminary phase, the looking what we have. Of course, do you know that Chile is a very active country with many large earthquakes, but also very small or moderated events that now with the modern digital data we can understand better. But maybe some of these moderated events that in the period of the analogical seismograph were not looking, we have to revisit again and understand better what is happening with the Chilean seismicity in a long period of time to understand better the seismic cycle. And the good news is that Chile has a monitoring system from very early, around 1908, were deployed the first seismological stations by Montesús de Valor, was the first director of the National Seismological Service. And in this map, is showed the station deployed in this time. And this figure was published in the first volume of BCCA in 1911. But if we look the seismic catalog, despite we have seismograph for many times, we can look that the seismicity in the analogic period of time is very sparse. We have very few events identified. For example, all the events are plotted here in the 60s, are very few, and in the 60s we have the largest event in the world, Valdivia earthquake, magnitude 9.5, and we can see very few reported events. Are these red dots are the epicenters, and of course for a magnitude 9.5 we can see that there is very few events identified. This start to change in the closer period of time, and of course after of the digital time, we have many events identified by days and even by hours at this moment. And this is a video, our warehouse, where we have the seismograms. All the seismograms are around 1943, and the last one at the start of the 90s. The big problem that we have is it's not a complete storage, because at the end of the 80s, a fire in the previous warehouse destroyed many seismograms. Then we have not clear what we have. That was the previous question to Sergio Leon. Anyway, I think that here we have probably some interesting things that we can look for. And the seismogram are stored in these groups for the station that is recorded and are grouped in several months of data. The workhouse also is a little messy. Then we need also a sort of this all this data. here is an example, the station Santiago in 1973. That is the seismogram that shows Sergio before. And here, a little video with Sergio when I start to look in the seismogram for the 11th September, the day of the coup d'etat in Chile. Then, of course, we can do several things with this data. Sergio shows an example looking for the ambient noise, because several of these stations are in middle of the city. Then we can do some work like this. At this moment, we also do a work with a visualization of the data, but of course, the next stage is digitalize this and looking some decrease in the ambient noise with work similar that work done during the pandemic period. And there is other interesting sequence recorded in these analogic seismograms, and here an example for the Valdivia earthquakes. And I put again a figure only to look that we know very few about the aftershocks and foreshocks of Valdivia earthquake. This is a figure from the work of Inés Cifuentes. He studied very well the aftershocks and foreshocks of this event, but he found very few, I think so. These are the circles and the square and the foreshocks and the aftershocks, because she used the teleseismic data. And the local data were not used because, well, there is very few data at this moment. But in the warehouse, we have one station that is located in Santiago. It's around here, around 400 kilometers. And these stations, we have data from some sequence of these Valdivia events. And here there is an example. This is the day before of 22 May, 21 May, where happened the foreshocks, the largest foreshock, a magnitude 8 event that were recorded in Santiago. And the next day happened the magnitude 9.5. And of course, was not well recorded this event, but also we have the day after, and we can see many surface waves recorded in this station with a very impressive amplitude. And if you can see here, also, of course, we have many aftershocks that any person have studied, I understand. And we do a very few work with a student and with the advice of Luis Rivera, and we digitalize these aftershocks that are in the blue colors. And I think that is very interesting because all these aftershocks, we can see clearly where is the P and S first arrival. Then we can have an idea where are located the early aftershocks of Valdivia earthquake. For example, it's something that we can do with this data, and it's information that is not made for this earthquake, that this is the biggest one earthquake in the world. And I think that here we have many things to do. At the moment, we did this very handle with no early warning, with no machine learning, with not too much intelligence. It was very handle and hard work to obtain these 10 aftershocks. Then this briefly presentation is only to show we have some data and try to convince you that we have some relevant information that is in this moment in the analogic seismograph that is in these papers, and maybe we can obtain there important information to understand better the subductions earthquakes and some characteristics of the Chilean subduction events. We can look, for example, some swarms that occur in the analogic period, Now in Chile, we understand that the swarms are frequently and occur mostly in the same place. Then we can look if this is occurred before. Other questions, for example, is the Valdivia earthquake has more clear precursors. We know that the day before we have an event magnitude 8, also some hours before a slow earthquake. But what happened 1 week or 2 weeks before Valdivia earthquake, magnitude 9.5? There is some purchase. Maybe looking this data that at this moment in this warehouse, we can understand this question or other questions that we can try collaborating this. For the moment, we have this data, but we need to do a lot of work that sort, organize, digitize. Then our message is if we can collaborate in this to try to find some scientific things about in this data, we are very, very happy to collaborate. Thank you.
Thank you, Sergio. The floor is now open for questions. From Lorraine, we have a question. Do you know of any particular records of significant events that might have been lost in the 1980s fire? Sometimes copies of these events are sent to researchers upon request, and perhaps they may exist elsewhere.
No, we don't have a very clear inventory about the seismograms that we have, but I think that is if in some moments some seismogram was sent to some research, this is our lost, and I think also that the other problem is the seismogram from the significant events. Also, the most probably are also lost because at some moment the research not necessarily come back with the seismogram, and these are more than 50 years ago. Then I think that the significant events are lost, and I think that it's very difficult now to try to obtain some analogic seismogram with some old events.
Thank you. We also have a question from Tim. Since you are planning to do ambient noise studies, is it your plan to at least scan all of the records and perhaps extract complete time series? What is your plan?
Of course, this is an excellent plan, but at this moment we have the interest to do this one, but we don't have any project to do this. But of course, this is the idea.
Great, thank you. I think we will be moving on in the interest of time to our next speaker. So thank you so much, Sergio, for that fantastic talk. Our next speaker is John Ebel, who is a professor of geophysics in the Department of Earth and Environmental Sciences at Boston College and a senior research scientist at the Western Observatory of Boston College. Additionally, he is also a former director of the Weston Observatory. Thank you so much for joining us, John. And without further ado, the floor is yours.
Great. So hopefully this is visible.
Yes.
This talk is going to be a little bit of a departure from talks earlier today and what I've heard in earlier days, in that I'm going to have no visuals at all. I'm only going to show words, but I think the words are important. And of course, there's something here that can be used if any of you are writing reports or thinking about the problems that we're dealing with. So I want to talk about the paper seismograms at Weston Observatory of Boston College. a seismic station that has been operating almost a century now. And I'm going to give you a little bit about the history of seismic monitoring at Weston Observatory to start. So in 1928, the Jesuits at what was called Weston College, which was a seminary for training Jesuit priests, here in Weston, Massachusetts, obtained a pair of 25-kilogram Bosch Omori horizontal seismographs. And they then proceeded to build piers in the basement of their college building. They broke through the basement floor. Fortunately, bedrock is right below the surface, so it's actually quite a good site, and it's kind of in a rather sparsely populated suburb of Boston. So the roads are small, and it's really been a good site for earthquake monitoring. Although they installed the instruments, they didn't know how to make them make them operate. So it wasn't until 1930 that a Jesuit from Georgetown University came to Weston and showed them how to set up the seismograph and get the adjustment set up and do the recording. So they started recording in December of 1930, and the first recording was in January of 1931. So the Bosch Omoris are mechanical seismographs that recorded on smoked paper. In 1934, they obtained an 80-kilogram Vickert seismograph, which also was a smoke paper recording instrument with horizontal instruments. And that became operational in late 1934. Important really for seismologists to know is that in July 1935, the director of Weston Observatory at that time ordered a set of what were then new Benioff electromagnetic seismographs from Hugo Benioff out in California. And those were received in 1936. The horizontals were received at a different time from the vertical, but they were all installed and were started recording later in the year of 1936. Those, I'll talk more about the instrument response in a moment, but from 1936 to 1962, those Benioff seismographs provided seismographic recordings that were comparable in quality, a little bit shorter period for the long period setup, but comparable in quality to the later WWSSN recordings that started in the early 1960s. And that's important because for those who want to study earthquakes from the late 1930s, 1940s, 1950s, and into the early 1960s, and want really good seismograms, those are available in the Weston Observatory collection. In 1962, the WWSSN seismic station WES was installed with short period and long period seismometers, as well as short period and long period galvanometers. And most people are quite familiar with the WWSSN instrumentation. Also in 1962, Weston Observatory began operating 4 remote telemetered short period seismographic stations that were installed in northern New England. So the data were coming back via telephone lines to Weston Observatory, and then they were recorded on 16-millimeter Develocorder film. And that network operated until 1968. 1975, the U.S. Nuclear Regulatory Commission was interested in earthquakes in the East and understanding the threat to nuclear power plants. And so they funded regional seismic network monitoring throughout the eastern part of the United States. Weston Observatory obtained funding for setting up that network here in New England, again with analog telephone telemetry and then into Develocorder recording. And that network reached a maximum of 36 seismic stations in the early 1980s. That network started digital recording on a PC computer with 16-bit digitization in 1996. And we still have those data. They're event detections, so we don't have continuous data, but we do have detections of continuous events, although These are just stored here at Weston Observatory. 2009, the USGS provided funding from a ARRA grant for replacing about 12 regional seismic stations with 24-bit RefTech digitizers and Trillium seismometers. And that network, once we installed it, then was taken over by the USGS in 2014, and they're still operating some of those stations today. I want to talk specifically about the Benioff seismographic system because those records are unique, very important, and there are a few researchers who have used those records pretty extensively in the past. Emil Ocal at Northwestern has used those. I recently had a request, for instance, from Hiro Kanamori for the records from an earthquake. He wanted to get the long period seismic moment, which I think he was able to do. So there were three sensors. They were a vertical and two horizontal Benioff seismometers, which were 1 Hertz natural frequency. And then the signals from those seismometers were split to 2 different recording systems. The short period recording systems had a galvanometer with, for the vertical, a natural frequency of 0.5 seconds, and the horizontals natural frequency of 1/4 second, so the equivalent roughly of short period WWSSN recording. And then the signals from each of those seismometers was also sent through a set of 3 galvanometers, each with a natural frequency of, a natural period rather, I should say, of 60 seconds. I don't know why I've got natural frequency here because these are the natural periods for all 3 components. Recordings were made on high quality photographic paper, and those seismograms are still stored here at Weston Observatory and are in very good condition today. Also at Weston Observatory from 1967 to 1987, we had a pair of Wood-Anderson torsion seismometers, horizontal recording, horizontal sensing rather, ground motion sensing with photographic recording, and those primarily recorded local earthquakes. There was a Jesuit who originally studied here in New England and then went to Kingston, Jamaica, where he installed a seismographic station and operated that until he left in 1966. Apparently there was no one to run the station after that, so he packed up all of the seismograms and brought them back, and those are also stored here at Weston Observatory. I can't tell you right off the top of my head what the response of that station is, but it may be just horizontal recordings. But even so, for the Caribbean region, there is a set of seismograms from the mid-1950s to the mid-1960s. One of the things we are interested in doing at Weston Observatory is getting all of these data digitized. Now, we have bought a single unit that we can feed the paper through and get a scan of the seismogram images. It's just wide enough that it will handle the seismograms, and then it just rolls through. And that's not a very fast process. And so for individual seismograms or individual sets of seismograms, that's fine, you know, like a day or 2 days worth of seismograms. But for large production, that's really not very practical, even if I had an army of students to feed the seismograms through the instrument, through the scanner. But just to give you an idea about how many seismograms we have, the smoke paper records from the Baushamori and then the Vickert, we estimate we have about 4,100 sheets. Each Baushamori horizontal component was recorded on a separate sheet, whereas the Vickert recorded both horizontal components on a single smoked paper record. The Benioff seismograms, I estimate we have probably about 57,000 individual sheets. There are 6 sheets per day, 3 short period and 3 long period. There were times when they ran actually at only half a day for a sheet to get higher resolution on the recordings. And then there were some days when they were short of paper where they ran double. They slowed down the recording so that they could get 2 days worth of seismogram on a single sheet. Estimate 57,000 of those. Of course, from the instrumentation from the WWSSN through 2010, when the digital station here, the 24-bit station, started running at Weston Observatory, we have about 104,000 sheets. We have about 15,000 sheets of Wood-Anderson records. I think we probably have about 4,000 sheets from Kingston, Jamaica. Now, in order to get these digitized, we have to know what kind of digital storage we're going to need. And I've tried to do a very rough estimate of this. We've done some scans with our scanner, and that has a maximum density, dot density of 1600 dpi, and scanning either a 24-bit color or 24-bit grayscale. The grayscale is a little bit less, but not that much less in terms of size per seismogram. I figure if we were to digitize all of the Benioff seismograms and all of the WWSSN seismograms, paper seismograms, through 2010, all of the components, those would in total take about 57 terabytes of data. The Wood-Anderson records, again, if we digitize at 600 dots per inch, would be about 6 terabytes of data. The smoked paper records, those records are basically half the size of the Benioff or WWSSN pieces of paper. So there's fewer of them, and then of course they would take up less space. Would probably be about 500 megabytes. Rough estimate for the records from Kingston, Jamaica would be 1.5 terabytes. And I would note that 600 dpi is the maximum that we can do with the digitizer that we have. I've been in contact and actually had some exchanges of data with Thomas Lee, who will be presenting later. He prefers 1200 dpi if at all possible, and 24-bit color digitization. And so if you go from 600 dpi to 1200 dpi, these numbers that I'm showing here are going to be significantly greater than the numbers would be significantly greater than the storage shown here. We have someone in our area at a company called Inception Technologies Incorporated in Manchester, New Hampshire, who is interested in perhaps digitizing the paper seismograms here at Weston Observatory. We got in contact with him because the head of information technology at Boston College knows the person who runs this company and knew of the company, and so he gave us their name and suggested we contact them just to get an idea about what the costs would be. So rep from, or the head actually of Inception Technologies, came to Weston Observatory this past summer. We showed them the seismograms, explained what we were looking for, and they have been in the process of evaluating their capabilities about doing this, and they've actually decided they needed to purchase some new equipment for doing this job. We were hoping to have a quote from them before this presentation, so that you would have some idea about what a commercial company would charge for doing the digitization of the seismograms. Unfortunately, they haven't given that to us yet, although about 2 weeks ago I did give them some seismograms to do test digitizations with. In discussing with them, they have also talked about not just digitizing the seismograms, but storing them and making them available to users globally through a public-facing website where users could go in and access the database and download the bitmap scans of the seismograms. Now, they would not be obviously vector seismograms, so you'd have to worry about that or doing that with other software. But they're also going to include that in the bid. We have no funding for this yet, but I did at one point talk to the president of Boston College, who asked me what it would cost to digitize the records. And when the president of your university asks that question, you want to give him an answer. And so that's why we have been involved in this exercise. Since we don't know what the number is, we don't know whether he would look at it and say, okay, yes, we can do that, or, fall faint on the floor. But there is a little bit of interest, and he's interested because he's a historian by training. And so he understands the importance of storing legacy data. Once we get that bid, we will share that with the university. We certainly are free to share that to anyone else who wants to know what it is. Inception Technologies sounds like they could see themselves turning this into a business where they might be able to do such digitization for other archives as well. So we're kind of a test bed for that. So that's all I have. I'm going to stop sharing and ask for questions.
Thank you so much, John. The chat and the Q&A are open if anyone has any questions.
And then let me just say that, if anyone wants to send me emails and ask questions offline, you're welcome to do that too. Mark Bain, who's now the current director of Weston Observatory, can also answer questions on this topic.
I'm seeing a couple of comments, one from Lorraine and one from Tim. Everyone seems very interested in this work, but I'm not currently seeing any questions. So if we don't have any questions, thank you so much, John. And I think, oh, sorry, Thomas Lee is asking, are there any thoughts on also digitizing logbooks and bulletins?
Logbooks are, if we cut them open, are easier to digitize. Bulletins, we actually, okay, so this is a sad story. So from 1975 into about 2008, I'm sorry, 1998 or so, Weston Observatory produced a bulletin of seismic recordings and earthquake locations for the northeastern part of North America. We included data from basically the Lamont network up through New England and into Canada, actually down to Pennsylvania, in fact. And we digitized, I mean, that's not a big stack of data. So we put it in Scan Digitizer, digitized all those data, posted it on the Weston Observatory website. Boston College, in its infinite wisdom, decided to redo all of its websites a few years ago. So they redid the Weston Observatory website and got rid of the digitized version of those bulletins. So we have to redo that, but that's pretty easy to do. We cut the bulletins apart, we put them into a scanner, and that's like a day's worth of work. There are some earlier recordings going back to bulletins rather, going back to the 1930s. I think all of those data probably were reported to the ISC. So the arrival times from the 1930s into the 1950s from the Weston station, I suspect you can find in the ISC bulletins.
Great, thank you. Thank you so much for that wonderful presentation. I think in the interest of time, we need to move on to our next speaker. Our next speaker is Wilfried Strauch, who is a German seismologist who works in Nicaragua as an advisor at the Nicaraguan Geosciences Institute. He is engaged in seismological research on seismic, volcano, and tsunami hazards and disaster prevention, supervises the development of early warning systems for earthquakes and tsunamis in the country, and cooperates also on a regional and global scale in the tsunami warning efforts of the IOC and UNESCO. Thank you so much for joining us. And without further ado, the floor is yours.
Well, thank you very much for giving me the opportunity to present our institution and our historical experience. The next, please. Well, in the moment, yeah, please, the next. Okay. You can see here what are the main products of our seismology department. We have an earthquake early warning system running for Nicaraguan, which is public since 2022. And in the moment, the number of people receiving our warnings is in the thousands, and we are working to increase these numbers to get really the possibility that everybody in Nicaragua gets earthquake early warning. The pre-warning times are between 20 or 30 seconds for big earthquake in the Pacific Ocean, until 0 if the earthquake occurs very near to your home or the site where you are. For instance, for us in Managua, it would be, we would not get any warning if there's an earthquake in Managua. We are working on tsunami warning for Nicaragua because we had a big tsunami in 1992. And we were able to establish tsunami warning system on the national level for Nicaragua in 1996. And we are responsible for tsunami warning in Central America since 2019. I have to mention that we have a very close cooperation and extensive data sharing between the Central American countries. We have direct access to stations in Northern South America and the Caribbean too. We are the Central American Tsunami Advisory Center within the Pacific and Caribbean tsunami warning systems of the IOC UNESCO, and this CATAC center is established at INETER Managua too. In real time, we have in Nicaragua 140 stations operating and sending us the data, and in total we get about data from 700 stations, mostly, of course, are not our stations, but from the other countries in Central America, the Caribbean, and also worldwide. Next, please. Here, two photos of our data center. We have two persons as watch centers working 24/7 system. And we have a group of 16 people capacitated for this work. The total number of people in the seismology section is about 20. We are using Seiscomp Pro with modules, among others, for moment tensor estimation and tsunami modeling or processing. It's completely automatic, of course, for early warning. So as I mentioned, within seconds. And we have a supervised automatic processing for tsunami warning. The first locations manually or supervised by a person, we publish in 2 minutes. We are also responsible for volcano seismic monitoring for the 6 Nicaraguan active volcanoes. So next. Okay, well, now how started this network? We had an earthquake, not too big, magnitude 6.2, in 1972, just before Christmas. And this earthquake killed 10,000 people in the capital of Nicaragua, Managua. You can see a photo. All the center of Managua was flat, besides some buildings which were newer and built from newer materials. The houses in Nicaragua and in Managua were mainly built by traditional materials. So we had a lot of adobe buildings, and all this crashed down, and many people died, not only by the houses itself or by falling down the things they had in the house, but also from fires which broke out in the town. Well, this was a good reason, of course, to start to build up a seismic network. Nicaragua got help from the United States. USGS people came and worked together with the Seismological Institute, which was founded in the same year, and initiated the telematic seismic network with up to 16 stations. All stations were installed in very quiet location, and the recordings were really excellent. The next, please. Well, within only 4 months of recording, it was very clear what was the cause of earthquakes in Nicaragua, which was not really known in this time. You could see clearly the depth distribution of the events in the subduction zone, and you could also see the events in the volcanic chain of Nicaragua. And this was very astonishing, well, for people in Nicaragua, of course, and also from the scientific point of view, it was a very interesting result we got in a very short time. A bulletin was produced and was then published yearly by the Seismological Institute in Nicaragua for about 10 years. Then we had an interruption due to the political development in Nicaragua. You remember we had a revolution in Nicaragua in 1979 and the Civil War. And next, please. But then we continued to work in the 90s. So the data system was, well, you had an old scheme. The seismometers were amplified, then the voltage was converted in frequency, transmitted not in a phone line as it is here in this picture, but by radio, was sent to Managua, to the Institute, and the recorder was used to generate the recording on 16 millimeters film. And it was possible within a few minutes after the earthquakes, actually to see the recording on similar projector, as you can see in this slide, and measure the time, the arrival times of the phases and amplitudes. Next, please. This system was working very well for the first years. And here's a description of the developer recorder. I will not explain more in detail. And next, please. We have still some of the old equipments in our storage. Seismometers were Mark L4 seismometers. The next, please. Now, this system was running well until mid-80s, end of the 80s. Then, while the cooperation with the United States faded out due to the political reasons, and we started, I can say we, because I came to Nicaragua in '89. we started to re-establish the seismic network in the 90s and were very successful. The people were trained. And we, in this time in the 90s, we also started to work with digital recording and so. After some years, we had a cooperation with the Swiss Seismological Survey, and they warned us that these developer recorder films could suffer from problems, which maybe in the photographic process could have occurred because it was not always as it should be. And they had experienced these problems and told us it would be a good solution to cut the films to enable easier coping and scanning of the waveforms later on. And we did it as they proposed. They helped us with some equipment, projector to see the data. And we had one person who was in the 90s still trained to use these films and knew to interpret the time signals and so. He worked several years, and at the end we had a lot of plastic sheets, next please, with the data, with the cut segments of the film. Here you can see, as we have it now, it's all the archive we have, all the events recording in the 70s, and a big part of the 80s are now in this small container. At the right, you can see the recordings. Well, it may be not so clear to see, but these are very fine lines and so, and you can get a very good idea of the seismograms. You can make a picking, but then if you next please, then it will be difficult to digitize the data. Well, I have to say all the events are processed already. The people made a good job in this time. The picking was excellent. The amplitudes were not evaluated, but the magnitude was determined from the duration of the seismogram. Well, I am in doubt whether these waveforms can be digitized. Maybe for some project it might be interesting. Next, please. Well, what we have is now the following data from the developer from 75 till 85. Everything is picked, and we have the bulletins. We have the data later on converted into SISAN format, and we have them in our catalog. We have the film strips and sleeves, but no film rolls anymore. So if there are events which were not detected in this time, they are lost. I have to say they did not process events outside of Nicaragua. So big earthquake, big global earthquakes or regional earthquakes are not processed, and we don't have the data anymore. They're lost. From 83, there was a little disorder starting in the institution, and the bulletins are not published anymore, but we have the data in the computer prints. So they are in our storage, but we have some also in a digital form, but not in the SISAN format. Then after 86, I'm not very sure, the data are rather incomplete, and the developer in some moment faded out. It was not possible to repair it, and people started to use helicopters with ink, or later on, there came also a recorder on paper, a continuous paper recording. Next, please. Well, as I need to digitize these films, for us in the moment, we do not have this interest, but that's why I present here. Maybe for other people, it would be rather easy to make copies, to scan the films we have cut in these sleeves. And well, we are very open for everybody who is interested, and they can contact me, and we will do what we can to help them. The next, please. Well, finally, remarks. Well, I mentioned already the developer coders and many stations did not work, and we started again in 1991, 1992, testing several new systems, digital systems. In 94, the system which came from the University of Bergen, Norway, we used for many years for central digitization and acquisition and size-un for processing. It was the main system for us until 2016, actually. We had many different systems for data transmission, even mixed analog digital systems from Japan. We had also Earthworm, the beginning of only for volcano stations, later on for all stations, replacing the QNX SizeCom. We started in 2004. In this time, it was only SizeCom for data loggers. And later on, when Potsdam, GFZ, which is, by the way, my institution where I was coming from, started to develop the system for seismic processing. We started to use it too, and from 2012, it's running continuously. In 2016, is it the main acquisition and processing system, and we started in this year to develop the earthquake early warning and tsunami warning systems. The next, please, the final. Well, first I have to thank the people from the Nicaraguan institutions who worked with these data and for many years did the data processing. US Geological Survey donated the equipments and helped a lot in the first years, but later on, when the political situation improved again, we had their help and their cooperation, especially the VDAP group for the volcano monitoring and early warning. The Swiss Seismological Survey for many years was a partner in cooperation for disaster prevention in the years of the 90s, 2000, and just now the earthquake early warning system for Nicaragua and for Central America we developed together with them. And I have to mention a friend and colleague of us, Mario Bordan from the Seismological Institute, who did all the work to cut the film rolls and to organize the data in the plastic sleeves. Next, please. Thank you very much for your attention.
Thank you. We have time for maybe one question, and then we have to move on. We have a question from Lorraine. For the cut develop quarter data, how is the metadata maintained, station channel, start time, etc.?
Yes, it's a very good question. First, each of the sleeves has a number. And this number, we have a list of these sheets, and this number is then connected to the event. And then we have the original bulletins, where we have the events with their epicentral, hypocentral data, and we have the size-un database with complete information, including also the phase data. Well, that means we have a system which permits to know which events are in each film strip, but there might have occurred changes in the stations, in the organization of the stations in the film. And I'm not sure whether we can easily reconstruct this. But it might be in some, it might be possible because you have the peaks. And while it will be very easy to identify the station knowing the peak time, I think. Thank you.
Thank you very much. We are going to move on to our final talk from our final speaker, who is Thomas Lee. Thomas Lee received his PhD from Harvard this past spring and is now a postdoc at Princeton. His interests are in rescuing legacy data and utilizing it for modern techniques, such as noise analysis. Thank you so much for joining us. And without further ado, the floor is yours.
Perfect. Thanks so much. To kind of wrap up this session, I want to talk a little bit about legacy seismic data from HRV. So for those unfamiliar, that is the seismic station in Harvard, Massachusetts, about an hour west of Boston, pretty close to Weston, actually, and what we've experienced with the data there. This station was put in with a vault in the early 1930s, and it operated until about the mid-50s before falling into disrepair. And eventually it was brought back with the early broadband work in the 80s and today is part of the GSM. But the short amount of time, relatively, where it ran as an analog station means that we've been able to go through more or less the full process of rescuing the data from this station, scanning it, developing an understanding of what the metadata is and what the relevant pieces are, storing all of this data and metadata, and then starting in on digitizing these records. And in this case, digitizing means taking these scanned images and processing them into seismic time series, waveforms in SAC or what have you. So the Oak Ridge Observatory is in Harvard, Massachusetts. And as I said, it was running for about 20 years in the early 20th century. And this head house here, you can see, was located here in the diagram, above ground with a stairway going down into the vault. About halfway down the stairs, there's this large wooden cabinet in which the legacy seismograms, the analog seismograms, were shoved into essentially after they had been analyzed contemporarily in the time that they were recorded. When the station was upgraded and renovated in 2007, there was a need to remove that chest of drawers and with it the seismograms. So the seismograms were pulled out of the drawers. In fact, the drawers themselves were pulled out of the chest of drawers and put into plastic boxes, figuring that, okay, we have these records now and we have support from the Harvard Library. So the thought was to go ahead and see if we could get help archiving these data. There were about 16,000 total, as some had been damaged beyond recovery while they were in storage or ended up missing before that even. Now, we hit a bit of a wrinkle because the Harvard Library essentially came back to us and said that, well, we won't touch these records. They are a biohazard. They are covered in mold and dirt and animal detritus, and you need to clean them first. And for that, we end up needing to clean the records. So there are a lot of bugs and stains. These records, unluckily, were not kept in nearly as nice a condition as it seems like some of the records that Sergio and John were talking about. And so there was a lot of damage control that had to be done. And to this, we are very thankful to the folks at the Wiseman Preservation Center at Harvard that really helped us understand how to take care of these records, how to perform some of this data rescue, and put us in touch with larger national organizations that are based in art conservancy. For example, the American Institute of Conservators, and in particular, since our recordings are mostly photographic, their photographic materials group that also were instrumental in helping us understand how to treat these records properly. So for those that may not have thought about it or are considering, that is also a resource that is out there. Okay, so now on to scanning. We used a Context HD Ultra for our scanner. And because we had about 16,000 records over the period of a couple of years, with the help of volunteers, we were able to go through and create scanned images for all of those records. In total, there were about 10,200 seismograms scanned. You might notice that number went down again because other records were damaged. The photographic emulsion oftentimes meant that the records kind of melted into one big block. So in the end, we end up with about 10,000 scans. And at this point in the game, we weren't sure what was going to be necessary to properly recover waveforms from these records. So we figured we'd start at the highest possible resolution and work down from there. And what that meant for us was to start with a lossless file format. So that would be TIFF and 24-bit color, 1200 DPI. And as you might imagine, this ends up resulting in quite a large file size. Each scan would be 1.6 gigabytes. And that's just the front. We also did the backs of each seismogram. These were done in 8-bit grayscale and at 400 DPI, simply because there was less detailed information that would be needed from the backs of the records. There are notes and some metadata on the back, so it's still important to scan them, but the resolution need not be as high. The net result for scanning the collection in this way is that we end up with a total file size for one station and for an incomplete record set that spans about 20 years of about 40 terabytes. And this is not exactly tractionable depending on what kind of data storage is available. And so as we started exploring digitization of these records and methods which we could use for that, and that's something I'll get into in a little bit, it was realized that if we convert them to JPEG files while maintaining the resolution of 1200 DPI and the color depth of 24 bits, then we can change the file format from the lossless TIFF to a lossy JPEG. And this makes a large difference. For each of those records, the file size drops down to about 50 megabytes, and the total size of the collection is going to drop down by orders of magnitude to about 470 gigabytes. I do want to highlight that as a part of scanning these, all these records are hosted on the Harvard Seismology webpage. And so these are freely available to go and download anything that we have from the collection. Now, I mentioned the metadata. So I want to spend a little bit of time now talking about metadata for these seismograms. And it goes a little beyond the things we typically think about with records. So certainly we have the start and end date, the type of instrument, and the direction of motion, what channel essentially we were looking at. But on top of that, when we look at these old seismograms, we're concerned about a couple of other things, including the time per trace. So for each line on this photographic helicorder, how much time has passed, as well as things like the timing errors or artificial disturbances. These sorts of things oftentimes are recorded on the back of the seismograms. Here's an example of one of the backs of a seismogram which we scanned. And you can see that written into the stamped template, they put the time corrections that were recorded with radio time at that point, as well as notes on just what different parts of the record were. Sometimes on the same sheet of paper, you would have both a horizontal and vertical component, for example, as shown here. Now, this information is important for just realizing what the data is, but collecting as much metadata as possible is also crucial to being able to utilize this data to its full potential in a modern sense. And for this too, we are lucky to have the logbooks from the Harvard station. Here's an example from just one of the pages, and crucially what it lists out is T0 and TG, the periods that were set for both the short period and long period instruments across all three components. I won't go into much more detail since John already did a great job of describing these Benioff instruments, which Harvard also installed when that new vault went in the early 1930s. So the reason that this is important is that when you have digitized data, you can start trying to think about things like, okay, let's make an instrument response to really try to use this data in a modern sense. When we digitize, we get amplitudes and pixels, and it would be really nice to get real units. So here's a quick example of how this might pan out. The blue curve here is a normalized transfer function, theoretical transfer function, which is derived from the periods T0 and TG as listed in the logbook. And what the black line is an empirical instrument response derived by comparing surface wave spectra for doublet earthquakes, where one earthquake was recorded in the 1930s at HRV, and the other was recorded at modern HRV, the GSM station. And you can see that there is good correspondence, but you actually do have a little shift in where the peak amplification is, as well as, not unexpectedly, an increase in long period noise. So while it's important to have these old data, it really is going to be important to have that to understand what we're actually looking at and how well we're doing when we are trying to use the data in a modern sense. This is a good sanity check, if nothing else. But we don't expect it to be exactly the same. That we're in the same ballpark for what they were thinking they were getting in the 30s is a really good sign. Okay, so the other thing metadata is important for is determining what kind of scanning resolution we should actually have. And this is a little bit circular because the scanning in some ways is going to give you the metadata. But this is why I want to present and make the case that thinking about scanning resolution and determining what resolution should be used is something that should be done before you start. And based on metadata, you can read straight off the record. For example, the length of each trace. So here we have the length of time, a distance essentially, on the piece of paper between 1 minute and the next. And this corresponds, of course, to a speed, which we should know from the old metadata, whether that be a logbook or just measure. And in this case, the rotational speed of the drum would be in centimeters per second. We can, of course, convert this to inches per second because the measurement, as we know, for resolution is usually pixels or dots per inch, and make the argument that, okay, what we are really trying to get at is a sample rate. So a number of pixels here indicated by this grid. And note that, this is just for demonstration purposes. We'd really be in trouble if this were the size of the pixels. But the idea is we want to get to a sample rate in pixels per second, just simply by multiplying this DPI with the rotational rate of the drum and the data rate, essentially, that was being written to the paper record. Now, if we take this kind of a dichotomy and say that, okay, samples per second can be walked back to the speed rate of the instrument for a short period record at Harvard, for example, where the traces are 30 minutes long, that's 1800 seconds. You can say that there is therefore 0.02 inches per second. Now, for a short period record, it would not be unreasonable to say we want to have sensitivity at 10 hertz or 20 samples per second, if we consider Nyquist. What that means is if we have 0.2 inches per second, and similarly we want to get 20 samples out of that 0.02 inches, dividing them through is going to give us a resolution of 1000 ppi that we would want to get to that sample rate. So that's a good reason, or a good basic kind of calculation one can do to say, okay, how long are the traces on the record, and what kind of sampling resolution do we eventually want to get out of a digital product resolution? Now, there's some argument to go higher, and for that, I want to just show a little bit of a set from DigitSize, our digitization software. The reason to go higher is that besides just having the sample rate and time, being able to clearly resolve the shapes of traces and do exercises for a complicated earthquake, like finding the overlapping areas, shown here in pink, such that they can be removed and the traces digitized properly, is always beneficial to have more resolution. And that is that leads nicely into talking about DigitSize itself. So this is a software based in MATLAB that we also make available on the Harvard Seismology website. And the idea is it will look for areas where there are traces and try trace through. So a couple of things to note here are that the time marks, these offset portions, have been reintegrated with the trace, and the information on the location of those time marks is used to generate timing. Now, this is not a fully automatic software, and the design goal was to get the highest accuracy possible out of an old seismogram. So there is human intervention required. But that being said, it works really well on things like noise. So Sergio mentioned earlier, talking about noise. That is one of the reasons that I have focused a lot of my other research efforts on seismic noise, since grabbing that for the 1930s with these Harvard records is fairly straightforward with DigitSize. Currently, support is for galvanometric or photographic records, in other words, records without curvature. But the upside is it'll take the time marks and it'll get a SAC file straight out of it. So we are working on DigitSize continually. And the next thing will hopefully be compatibility with developers, which also got mentioned a little today. So to sum things up, we have a pretty small collection at HRV, but the nice thing is that it has given us experience on more or less the full process of legacy data rescue, and also an understanding and start into analyzing what we can do truly with this data in a modern sense. Current challenges, of course, include recovering and standardizing metadata. We continue to explore what kind of metadata is going to be necessary to truly utilize this data in a modern sense. Continually improving digitization. I want to take a little time here to also make the point that scanning at a high resolution and making sure to hold on to those scans is really important, because this is essentially the new raw format of the data. There's a time sensitivity to these matters, because these are physical materials which are degrading in time, and trying to get a snapshot, a digital snapshot in time, is really important. 10 years, 20 years down the line, it's very likely that with things like AI and machine learning, computer vision, the digitization part is going to get much, much better. But we want to get as nice of an image of these records as we can now before they physically deteriorate. And then, of course, securing appropriate storage for both physical and digital records is of utmost importance. We have a small collection and a supportive library, which was really great at Harvard, but we need to explore other resources as well. Mentioning noise and climate dependence, how we can look at things like ocean wave climate with seismic noise. This is a really unique data set for things like that, and exploring avenues to figure out what kind of data centers might be more willing to host long-term continuous data for those kinds of purposes is something we need to be doing in the community as well. The upside is that there's a huge amount of promising future work which can be done with this data. It represents a really invaluable set of information. And with that, to wrap it up, as I'm over 15 minutes now, thank you all for your attention, and take any questions that folks have.
Thank you so much. I see we already have a couple of questions. So we'll take the 2 questions that are here, but we are a little over time, and we're going to transition after these questions directly into the discussion session on physical records. So the first question is from John. Could the increase in long period noise in your comparison of theoretical and observed response be due to warping of the paper seismogram, which could show up as apparent long period energy in the seismogram?
That's a great question. Potentially, because of course these are heliquarter records and the paper is warping, as John mentions, over time, that's a real possibility. And one of the struggles with this old data efforts are to try and really carefully construct the zero line for the record. That being said, when we do this analysis, we're taking a fairly short time period, about 10 minutes, and we're making sure to do a non-parametric detrending. So in this case, probably not, but I wouldn't rule it out completely.
Thank you. From Lorraine, is there any impact in the final time series when starting with a TIFF versus JPEG image? I note that some image processing software needs a TIFF image.
What we've noticed, and with what we've done so far with Digitize, is that there isn't a significant impact at all to using a JPEG. And my best guess at this, though I'm no expert on digital image formats, is that what the TIFF is preserving when it's lossless is a lot of small variations in the paper itself, specks of dust and that sort of thing, which is in the background. What we really care about is a much more smoothly varying and large-scale feature, the traces on the image. So I think using the JPEG is a pretty reasonable thing to do. What is really important, I think, or what is really more important than lossy versus lossless format is the color depth and the resolution.
Thank you. Another question from Tim, a somewhat religious question. Once scanned at, say, 1200 DPI, would you still want to retain the original analog recordings?
That's a great question. And I think I'm going to just use 2 analogs to give a roundabout answer to that question. One is something that was commented to me at one of these photographic meeting groups with the art conservators. And someone came up to me kind of confused and said, well, why are you guys trying to digitize all these records? You should be investing in flood-proof basements with humidity and climate control, because preserving those physical records is going to last for hundreds of years. And if you convert to digital, there might be a power outage and it'll be gone in 10. So I think there is, there's that aspect too, where we kind of need to think about what's the longevity, but realistically, the first priority should be to scan all these images, just because that's where they will be useful for science. If it's at all possible, I think it would be really valuable to be able to save the analog recordings, save the originals, because the same thing goes for scanning to a lesser degree than the digitization, that the technology for being able to do that might also get better. So as much as is possible, it would probably be a good thing to save those recordings. The other flip side to that is that, there's the space issue as well.
Great, thank you. And then we have a final question from Mark. Is there a maximum resolution that makes sense for a specific analog record based on, for example, pen width?
That's a good question. There's that other dimension that I didn't really talk about. I talked a lot about pixels and time. There's also the height of the trace in some ways. That's the pen width. And well, yes, you could try parameterize it by the pen width. That probably is a lower bound that you'd be getting using that, using that number, because essentially what we're doing is taking a median or an average or some kind of relationship between the lower and upper bound of the trace itself. So even if a variation in the seismogram is much smaller than the pen width, we can capture that. So the pen width is maybe not a great parameterization compared to timing sampling for the resolution. But I think that pragmatically, with the size of these records and the types of scanners we have today, I'd say 1200 is honestly probably a realistic upper limit. Not necessarily technologically, but the time that it takes to make each of these scans also increases with the resolution. And I don't think we've come across a case yet with our records where we've said, oh, we really wish we scanned this at a higher resolution than 1200. It's been sufficient for anything we've tried to do so far.
Great, thank you. That was our last question. So I would love to give all of our panelists another virtual round of applause. Thank you so much for taking the time and joining us. Clearly, this was very interesting to everyone, given the amount of questions and discussion we still have. Without further ado, we will be transitioning into our discussion session on physical records. And so that we can see everyone face to face, this is using a different Zoom link. So it's a regular Zoom meeting, so we can have more of a discussion. And I just put that Zoom link in the chat. Since we went a little over, we're going to take a little bit of a break so everybody can stretch the legs and get another cup of coffee. So let's reconvene using this new Zoom link in about 5 minutes at 9:44. Thank you so much. We look forward to seeing everyone in about 5 minutes. And thank you so much for joining. Have a great rest of your morning.